you could do. I mean, this is how, like I said, Vegas keeps track of games like craps, games that use dice. They have to know all the outcomes on the dice. Okay, so there's fair dice. Here's what I got for the blue distribution. Does this match what you guys are getting for your blue distribution? Yes. This is kind of a fun skewed left. A lot of data on the right. Drives the average up to about 8.2. You got a sigma about 2.6. A little more spread than a fair set of dice. If you don't have these particular dice, don't worry. I don't want you to copy these five. I'll have these posted for you so you can have them later. So that's what the blue dice look like. Here's what the yellow ones look like. This is kind of like a reverse image of the blue ones. It's skewed the other way. You've got heavy on the left side. And you'll notice that you can't get certain sums, like Jamie pointed out. You can't get a 10, you can't get a 12, so you just read those blank. I got a 4.5 average and a 2.2-ish standard deviation. Match roughly what you guys got? Somewhere in that ballpark? Yeah. Ballpark. It could, if you're off by one number, your sigmas and mu's are going to be off by a smidge. Don't sweat that too much. As long as that graph looks essentially like what you guys got, I'm a happy guy. There's the green one. Kate asked a great question. What shape would you call that? I called it the flipping the bird distribution. I don't know what it's called. What I was trying to do with this, though, I'll show you how I actually created these. I set up an Excel spreadsheet that basically randomly generates 1s, 2s, 3s, 4s, 5s, and 6s. And I just kept pressing F9 until I saw shapes that I liked. And then I built those dice. And what I was trying to do, that's a pretty cool one. What I was trying to do was to get a distribution that did this, which is called a Weibull distribution. Why couldn't I? I was trying to get a U-shape. That's what the green one was the closest I kind of came to a U-shaped distribution.
Two dice, so the ones in the middle. So am I on the right track?
You are, JC.
So when you add them together, they're...
That's the problem. If I got a bunch of 12s and a bunch of 2s, what do I also have to have by definition? A bunch of 7s, don't I? Because 12s are made by 6s, and 2s are made by 1s, which means there's have to be a possibility somewhere of a 6 and a 1 landing together, which would be a spike in 7. So this is about as close as I got to my U-shaped distribution without messing with my 1 through 6s. I could mess with the dots, but I didn't want to do that. So I got an average of 7 with the green distribution. It's perfectly symmetric. Notice the standard deviation is wider than it was on the fair dice. Hopefully that makes sense. The fair dice look like this. Why is this one standard deviation higher? Say that again, Jamie?
They're spread out.
They're more spread out. The data's more varied. You've got more in the tails than you had on the normal fair dice. The fair dice only had one outcome of snake eyes and one outcome of boxcars. This has 4 of each. And since those are the furthest elements away from average, by definition, the standard deviation has to be up because you've got more distances that are larger. Thank you, Jane. Perfect. Here's orange, one of my favorites, just a silly distribution. Bimodal, big gaps, and this is where we lost our 9. Here's a damn 9 right there. But bimodal, look at the average. The average is 7. Again, one of those things. There's your average. Hardly describing what's going on, but that is the average. That is the average of the distribution. Standard deviation is 2.15 for what it's worth. And there's the red ones in the back. Forget the 6, there it is right there. So this was the only one that kind of looks like the distributions we've been looking at recently. So if you guys had the red dice, you had this. Now, this was all great. This was all fantastic to be able to pull these distributions out of those dice. And I know that each of you only had one of those sets of dice. What I'm going to give to you now is a quiz that you're going to do with your partner. It's an in-class quiz. Because what I also just gave you was a bit fictitious, wasn't it? I gave you a pair of dice, which would essentially, if you will, be your population. Here's how your population behaves. So what I essentially let you guys just do is call a census. I let you analyze every single outcome of your population. Well, that's a little bit fictitious now, isn't it? Can you actually do that in a population? Can you analyze every single element of your population? Oh, hell no. That's why this class is called statistics. That's what you actually analyze. Now sometimes we get away from that and we talk about mu and we talk about sigma because we have a probability distribution, and that's all fine and dandy. But what this is going to do is it's going to give you your first taste of 244. So, here's what I want you to do. Oh yeah, so said Robert. Oh yeah. Oh, it's okay. Well, this is your only taste of 244. All right. Here's what you're going to do. Instead of being able to look at all 36 outcomes, you're going to roll your dice. So Megan, this is what you and Harrison were doing earlier, where you were rolling the dice and keeping track. Now you're going to do that. So what I want you to do is, and you're going to be rolling them a lot, you're going to roll your dice 100 times total, but you're going to break them into groups of 4. So here's the deal. If you read the first couple directions, it says circle with the color of the dice you have on the quiz. So your first question is just draw a circle around your dice. Then it says roll the dice 1 time and just keep track of the sum that you get. Okay, not in the chart that's below, but just somewhere, whether it's in the TI or on a piece of scrap paper. Then you're going to roll them 3 more times. So you're going to have 4 total sums. So you're going to have 4 total sums after 4 rolls of 2 dice. Then you're going to average those 4 sums. And that average is what goes in sample number 1's X bar, is the sample average of those first 4. So you're drawing samples of size 4 from your population. Roll 4 times, average right. Roll 4 times, average right. And that's why you're doing 100 rolls total. Sample size 4 times 25 gives you 100 total rolls. Does that make sense? Yeah, hopefully that makes sense. If it doesn't, I'll wander around and work with you. But that's all you're going to do. So, and then complete all the way down to the end of page 1 with your little duet. And then once you get down to the end of page 1, we'll regroup and we'll talk about where we're going from there. Cool? So that's part of the picture.